applications into the flexible polyurethane foam and rigid polyurethane foam and so forth. So just ICL at a glance. ICL Israel Chemical Limited, with our global headquarters based in Israel. We are a global company. As you can see on the slide here, we are a multi-billion-dollar company in sales. In 2023, we had more than $7.5 billion in sales. We have manufacturing sites all over the world, and more than 90 plus years of experience with uh, more than 12,000 employees across the globe. And across the mineral portfolio, we are the top industry leader. And industrial products is one of the group within ICL that focuses on minerals that goes into the industrial application. Here we are mainly focused with bromine and phosphorus-based products and quite a few small like magnesia, etc. as well. And the flame retardant group is part of the industrial products division at ICL. Again, we maximize our R&D to develop and deliver complex solutions for various end applications. Just to give you a little bit more insight, in 2023, Industrial Products Group had more than $1.2 billion in sales. We are a leader in mineral portfolio. Again, like I mentioned, mainly bromine, phosphorus, and magnesia, etc. And we have manufacturing sites worldwide as well as part of the Industrial Products Group. In 2023, if you see on the slide on the right-hand side there, by region, the sales-wise, the biggest region that we play in is mainly North America, Europe, and Asia in terms of region. And if we look at the products that we offer, again, like I mentioned, bromine is one of the key minerals that we work with. And besides that, we have phosphorus and specialty mineral. Again, bromine being the largest chunk, about 63% of the total sales of the products that we are offering. And just for everyone's reference, we get our bromine from Dead Sea in Israel. So if you are familiar with Dead Sea in Israel, well, typically, people know or tourists know that you won't sink. So basically, you float, even though you don't know how to swim. It's such a high bromine-containing water in Dead Sea. It just makes you float. So that's where we get our bromine from. So now, next few slides will focus on mainly the technical discussion about flame retardants, how do they work, and polyurethanes and flame retardants for polyurethanes. So in this slide here, picture on the left shows you the triangle or the three main components that's needed for a fire to happen and or initiate and continue. And three components here are basically heat or temperature, air, which basically brings in the oxygen, and fuel. And in case of polyurethane foam, which is organic material that works as a fuel. So basically what happens is because combustion is a self-sustaining free radicals branching process, flames are very difficult to extinguish. So there is no single commercial flame retardant which provides just one mode of action. So there are different mechanisms. Based on that, the flame retardants are working in any given end application. So, for example, you have free radical scavenging, you have cooling flame retardant, you have diluting the fuel flame retardant that decreases the fuel supply, flame retardant that mass transfer and heat transfer barrier, so it creates a barrier and reflecting the heat of the flame. So just to give you an example, basically when you have the right temperature and in the presence of air, what happens is the fuel starts burning. And burning meaning it starts breaking down. So in this case, polyurethane foam, which is a polymer, which starts breaking down and starts creating the free radicals. And those free radicals keeps going back into this whole process again and continues the fire. So if you have a flame retardant that helps you with basically scavenging those free radicals, that's what the flame retardant mechanism is. So normally, again, giving a little bit of example, halogenated flame retardant, the chlorine, the bromine kind of atoms, those are the ones that work as a free radical scavenging kind of flame retardant. Then you have flame retardants that cools down the flame, meaning brings the temperature down. So if you don't have the right temperature, the fire scenario will not continue. So there are flame retardants that basically releases water during the heat process or the fire process, and that helps bring the temperature down, or that works as a cooling of the flame. Then there are flame retardants that basically dilutes the air. And what happens in those scenarios is basically the oxygen that's available from air is no longer available at the same rate that can sustain the fire. So again, different mechanisms, different flame retardants come into the picture, and helps with either slowing down the fire or eliminating the fire. But again, the three things that need to keep in mind here: for fire to happen and to sustain, there needs to be a heat or temperature. There needs to be an air source of air, and there needs to be uh, fuel. For polyurethane's case, it's foam. And the another example I want to share is, like the barrier, one of the bullet point here mentioned in terms of mechanism is the some flame retardants create a char. So what it does to is it creates a barrier, and what the barrier allows the mechanism to happen is where heat is no longer transferred from the environment into the polymer, meaning the polymer is no longer breaking down. Also, if the polymer has broken down, the free radicals are no longer allowed or stopped to get into the environment where it can mix with the air and the temperature and continue burning. So what we in polyurethanes world, what we you may hear more about charring. So that's what that barrier is. The char barrier creates a protective layer on the polymer that will avoid continuing the fire process. So that's a little bit about the general modes of flame retardants and how the fire works. Um, so as we work on designing the flame retardant and we look at the overall process of the fire, one of the things is the ignition. So ignition is the most important event in the course of fire. So if you don't have any ignition, there will not be any fire. So that's the initial part of the process where the temperature is still low, but enough that it can initiate the fire, and it is part of the fire process. In this diagram here, as you can see on the left hand side, it's where it's the ignition part, where if we are able to prevent the ignition, it will not continue and create a large fire, which could turn into a casualty and great loss. Again, the flashover is the point where the polymer and the mechanism is no longer able to control the fire. So at that point, fire is going to continue unless the firefighters get involved and all that. So on the ignition part is where we normally focus, and again, over there we try to either protect the polymer from the temperature and air, or try to bring the temperature down, because depending upon the end application, air is where we may not have too much control, or oxygen, basically, where we may not have too much control. So flame retardancy involves basically disrupting of the burning process at one or more stages. So like I mentioned, the ignition is where we are primarily focused, and focusing on preventing the ignition. That's the primary purpose. Or the progress is terminated within an acceptable period of time. So meaning, before we get to the flashover, if we can reduce the rate of flame spread, uh, avoid or delay the flashover, then that would certainly help with slowing down or controlling the fire in a manner where there is no significant harm to the humans and the properties. So again, kind of just repeating a little bit on what I mentioned in the last slide there. So roles of flame retardants. So there are many flame retardants are specifically designed to extinguish small accidental fire. And again, in this case, again, if we do not have the ignition, then the fire will not happen. So no ignition, no fire is the best strategy to mitigate the fire hazard of polyurethane foam. This is the strategy that's most efficient in automotive and furnishing, and it significantly decreases the risk of fire during the construction or renovation projects in building and construction industry. Again, decreasing the extent and slowing down the flame spread is often higher priority in insulation foam. So again, now we are talking about the second stage where ignition has already happened. Can we decrease the extent and slow down the fire spread? So in this case, we are not avoiding the fire, but what we are providing is more time for the building occupants to get out of the building into a safe environment. So again, it's slowing down part. It just helps with the evacuation part of the building and help with the save of human lives. And flame retardants again play here important roles. So some of the test methods that you may have come across focuses on both of this part, basically on the ignition part, if no ignition or slower ignition, and then the flame spread part. So how long does it take to get to a point where it's spreading all over or flashover has happened. So again, flame retardant mechanisms and the fire safety standards kind of focuses on these mechanisms to have the proper fire safety in any environment, whether it's automotive or building and constructions with furniture and etc. in residential or commercial buildings as well. I'm assuming that with most of you working in the polyurethane industry, you are familiar with TDCP and TCPP. So these are the two commonly used flame retardants in polyurethane industry today. And again, like I mentioned in earlier slides, the flame retardants are mainly added in polyurethane foam applications where fire safety standards needs to be met. So again, in flexible foam or in rigid foam, flexible foam that mainly goes into automotive or furniture, you would have appropriate safety standards, or in a building and construction industry, you would have appropriate safety standards that needs to be met. And that's where the flame retardants comes into the picture. So one thing I do want to point out is, can you make flexible or rigid foam without flame retardant in the formulation? Yes, it's entirely possible, and there are many end applications where flame retardancy is not needed, and so flame retardants are not used. So again, what drives the use of flame retardant is need to meet appropriate fire safety standards. Now coming to TDCP and TCPP, as you can see on the slide, if you just look at the chemical structure, both are very similar. The key difference between the two, between TDCP and TCPP, TDCP has two chlorine molecules on each branch on the phosphorus molecule. Compared to that, TCPP just have one chlorine atom or chlorine molecule on each branch from the phosphorus atoms. So that's the key difference. So TDCP, tris 1,3-dichloro or 2-chloro isopropyl phosphate, and TCPP, tris is 1-chloro isopropyl phosphate. So sometimes you may hear monochloro as well. That's the same thing. And both of these chemistries, both of these molecules are under heavy scrutiny from public and governmental agencies over the many years. And this is again, part of the broader scrutiny that the public and government agencies are doing on all the chemicals, including flame retardants. And there is a growing concern about chemical exposure and their migration into the environment. So again, one thing I want to point out is that you can see both of these chemicals, TDCP and TCPP, or both of these flame retardants, there is no hydroxyl group, meaning it's not reactive. It will not become part of the polymer. If there is no hydroxyl group, it would not react with the NCO, make a polyurethane or urethane linkage and become part of the polymer. So in other term, both of these are additive flame retardant. So both of these flame retardant will become part of the polymer, will stay in the polymer, but it's not reacted in, meaning it has the potential to come out or leach out of the polymer over time. And as it comes out and leaches out of the polymer, it would enter into the environment. Environment meaning air, water, humans or animal cells. And that's where all the challenges that starts coming up for any chemistries like TDCP or TCPP, more of an additive flame retardant. Next few slides, I will have a regulatory update. So like I mentioned, being additive in nature for both of these flame retardants, creating a lot more challenges. And that's where the regulatory bodies are coming into the picture and have restrictions or scrutinizing both of these molecules today. So as we speak, TCPP is currently classified as a category 1B carcinogen based on the existing data. And what does that 1B mean? Meaning it's a suspected carcinogen. A couple of years back, NTP, National Toxicology Program in the United States, done by EPA, which is the Environmental Protection Agency in the US, which kind of looks at all the chemistries, chemicals that's being used in the US and come up with regulations on the certain chemicals based on the um, toxicology profiles. So NTP ran a carcinogenicity study, and the results showed some evidence of carcinogenicity on TCPP. And based on that, the category 1B classification came about. Also, TCPP has the read across or structural similarity. So, in the last slide, like I showed you, the difference between TDCP and TCPP is only the one chlorine atom per branch. And there is another molecule which used to be part of a polyurethane value chain, TCEP, and that has been already phased out mainly in the US and in Europe because it's a non-carcinogen. So again, the structural similarity comes into the picture when the legislative body, when the politicians are coming up with the regulations. So it's more of driven by the emotions, not purely on the science based, but they look at the structures. They are similar, and they say if they are structurally looking similar, they should have the similar toxicology profile, and so that plays a big role when the chemical agencies are looking at these things. So as we speak again, Denmark in Europe has proposed for a new classification for TCPP in first quarter of 2025. And this classification is basically carcinogen category 1, reprotoxic category 1, and endocrine disruptor and human health category 1. So with all these classifications that Denmark is pursuing, even one of the classification is been approved by ECHA, which is the European Chemical Agency. Uh, this chemistry will be on the path to phase out and ban. So again, ICL being involved in the flame retardant industry for many, many decades, we know how this process goes. So even the starting of the process or the proposal for a new classification tells us that there is a sunset date coming up in the near future for molecules like TCPP. Added to, besides that, TCPP is already added to the POP screening list. Persistent organic pollutant is POP. And so now it's under scrutiny by the International Carcinogen Priority List as well. Washington State in the US, where Department of Ecology is reviewing organophosphorus retardant, flame retardants, organohalogen flame retardants, particularly in insulation under their safe consumer product regulation. And TCPP is part of that, so it's under scrutiny. TCPP in the state of California and the CDC is doing biomonitoring on that, being most ubiquitous in people. And what does that mean? So again, it goes back to my earlier comment, being an additive in nature for the polymer. Flame retardants like TCPP or TDCP has the potential to come out. And as it comes out, it becomes ubiquitous in environment, meaning it's being found in the water sources, whether it's a lake or a river. It's being found in air. So, there are plenty of NGOs, non-governmental organizations, are doing studies where they study the air in a car, for an example. They study inside air in a residential building or a commercial building, in schools, etc. And they are finding these chemicals, these molecules. So that's where it comes now ubiquitous in nature. It's being found everywhere. And besides that, there are so many other ways they look at the presence of this particular chemicals. So to support the TCPP ubiquity claim, there are researchers who are saying they have found it in breast milk, they have found it in fish, in household dust, indoor air, surface water, etc. So again, that supports that ubiquitous claim, which is not supporting the use of TCPP in the long run. There are already ban on use of TCPP in toys and total goods, banned in eco labels based on the halogen content. So there are a lot of ban already for TCPP, and there are a lot of scrutiny, and there are a lot of regulatory activities happening that would restrict or phase out the use of TCPP in the near future. Now, this update was more from the Europe and from the US, but bringing home to India a little bit, this is an article from the Times of India in September last year. This article is, again, I'm sure you will be able to find it. I can share the slide and you can read it through. But what I want to point out is uh, the data generated in outside India. So, for an example, particularly, in the last paragraph here on the slide, uh, what's pointing out is the research that was done in the US, where they are finding TCPP in the car. So basically, inside the car, they take the samples of the air and they analyze it. And they're finding TCPP, and beside that, they're finding TDCP and TCEP. So again, what's happening across the globe does have an impact. So today, India may not have any restrictions on TCPP, but if TCPP gets phased out in US or in Europe, then certainly, in India, you will see regulations coming up which would restrict or ban the use of TCPP. So we are working in a global economy, in a global environment where what's happening in the US and Europe would certainly have impact on chemical usage in the in Indian market as well. So now switching gear a bit to TDCP. Again, quite a few of the challenges are very similar to what I just mentioned about the challenges for TCPP. So TDCP is already on a Prop 65 list. It's a list in state of California where any non-carcinogen to state of California gets listed. And so TDCP is a non-carcinogen in state of California. And what that means is you would have to put a label on the product. So for an example, if you are selling a furniture foam or a chair in state of California, and the foam inside contains TDCP, you will have to put a label on the chair saying this chair contains a chemical that's that's a carcinogen as known to state of California. And those labels basically kind of affects the consumer behavior, and consumers would avoid buying such products if there is an alternative product that doesn't have such labels. Similarly, GETSL, it's a global automotive declarable substance list that's more related to the automobile or automotive market, and TDCP is listed on that. So again, automotive OEMs would have to declare that the products contain TDCP. In state of California, again, there is a state bill 1019, which demands the manufacturers to state on the label the product contains flame retardant. So now that's not just limited to TDCP. Any flame retardant, if it's present in, for an example, polyurethane foam, then there needs to be a label. So again, now if you think about it, uh, if the foam has TDCP, then it needs to have two labels. One is the Prop 65 label. The other one is this demand for the California State Bill 1019. So there are more labels, more notices about the chemicals, then again creates a negative perception in the consumer's mind. And so what we are seeing is basically automotive OEMs and the value chains are moving away from TDCP. There's still use of TDCP quite a bit, but then depending upon the end application and the requirements besides the flame retardancy, we see a lot more movement from the value chain just to start moving away even today, even though there is no phase or a phase out or ban on use of TDCP. Again, similar to TCPP, um, against TDCP. Denmark has proposed a new classification in 2025 Q1, and this classification is mainly focused on endocrine disruptor and human health based on the data already available. So again, if this classification goes through, we certainly feel that in a shorter time period, TDCP will be on a restrictions of use, and that will turn into a phase out or ban of this particular molecule as well. And besides that, TDCP has been under pressure from NGOs, institutes, and authorities since 2010. So it's not that these things are just happening in the last 1, 2, or 5 years. Quite a bit of all of these activities has been happening for last 15, 20 years. But again, it takes time in terms of the regulatory world and the advocacy world to and the legislative world to come up with the ban or phase out, because they will have to have enough technical support or the data supporting the decisions. Similarly, like TCPP in certain applications, TDCP is already banned. So from furniture, from children's product in many US states, and toys, etc. And like I mentioned, it's a very in various EU directives as well, and national regulations. This particular chemistry is already restricted related to young workers, exposure levels for the workers, pregnant women, and so forth. So again, a lot of things happening for the molecules like TDCP and TCPP that's widely used today in the polyurethane foam world. Now, coming to the end application market, where what drives the use of flame retardant. So again, like I mentioned earlier, you can make polyurethane foam without flame retardant. The main reason flame retardants are added is because there is a specific requirement based on the end application for fire safety, and that's what drives the usage. So if you look at the automotive foam, the key fire safety standard there is FMVSS 302, which is basically Federal Motor Vehicle Safety Standard 302, which originated in the US, and now it has become more of a global standard. And it's been used by the OEMs across the world. On the furniture foam side, that's another big market for flexible polyurethane foam. Depending upon the region, there are different safety standards. So, for example, in the US, we have California 117. And 2013 is the last revision. That's when the fire safety standard was revised. California 117, and then the other one is California TB 133. And these are just two examples. There are many depending upon, again, where the furniture foams are used in the final environment, meaning whether it's a residential foam, whether it's a commercial building, whether it's prisons, and so forth. In Europe, for an example, the key fire safety standard is British standard, BS 5852. You may have heard of as a CRIP 5 standard. So again, in BS 5852, there are different sources of ignition or heat. And CRIP 5 is the source of ignition or fire is what's used for polyurethane foam per BS 5852. And so again, depending upon different fire safety standards, there are different flame retardants that comes into the picture to meet those requirements. So in this slide, kind of summarizing all the things that I mentioned earlier, different regulatory challenges for TCPP, different fire safety standards, different mechanisms, how fire retardants work. And besides the fire retardants, the other criteria that's needed for the end application, for an example, humid heat aging requirement of the foam, VOC and emissions requirement of the foam. ICL has developed various flame retardants in basically last 25 years. So one of the things that we have heard over the years is, again, the negative perception about halogenated flame retardant. So there you will see there are a lot of flame retardants are basically developed as a halogen-free, non-halogenated flame retardant. So as you can see in the slide here, at the bottom I have listed the legacy products, which are basically, like I mentioned, the TDCP, based flame retardant. ICL sells that under the trade name of Firol FR2 or Firol FR38. TCPP, which ICL's trade name is Firol PCF or Firol PCF LO. And Firol 6 is a halogen-free reactive flame retardant. We see a small amount of use of that in flexible and rigid form. But besides that, based on the customer needs, the market needs and trends, we have developed various flame retardants. But as you can see, all the flame retardants on the top are halogen free. So again, coming back to the market trend, the market needs are more of a halogen free flame retardant to avoid that negative perception of the halogenated flame retardants. So all these flame retardants are halogen free. Some end applications require a more stringent VOC and emissions criteria. So to meet certain requirement, we have products particularly developed. So for an example, here is PNXLE. It's a halogen-free flame retardant, and it's very, very low VOC and emissions. And over the years, we have phased out or discontinued various products as well in favor of other flame retardants. So for an example, we no longer support or sell HF4, HF5 in favor of our next generation technologies. And also, besides the halogen-free flame retardant, the other part of our focus always has been if we can provide a reactive flame retardant. So again, coming to my earlier comment about the additive nature, now contrast to that, reactive is basically a flame retardant where we can provide a hydroxyl group, hydroxyl molecule, atom on the molecule itself. So now it works as a polyol, or it behaves as a polyol, and it would react with the NCO, and it will make a urethane linkage and become part of the polymer. So once it's part of the polymer, you no longer have the potential for it to come out of the polymer and see all the challenges or face all the challenges that's being faced by TCPP or TDCP today. So halogen free, reactive, and in certain cases, if we are not able to offer reactive flame retardant, then our target would be more of a polymeric flame retardant, meaning higher molecular weight compound. The advantage of such compound is being a higher molecular weight, the potential for it to come out of the polymer is very, very low to minimal. Again, they stay in the polymer, even though it's not reacted in. And even if they do come out, being a higher molecular weight compound, the potential for it to go through an animal cell and get digested or broken down would be very low. So it will, for an example, it may enter into the human body, but it won't get digested. It won't be broken down. It will just pass through the human body. And so the impact on the humans or any living organism will be very, very low to none for a polymeric material. So those are the key strategies that we look at as we look at the next generations of flame retardants. So again, I just want to kind of repeat that: halogen-free, reactive if possible, and if reactive is not a possibility, then polymeric material or high molecular weight compound would be our strategy in terms of the flame retardancy. So again, this is, in this slide is more of a development and innovation of last 25 years. But if we look at today's product portfolio and the market needs, we have kind of eliminated some of the products in favor of the next generation technologies. So FR2 or TDCP, like I mentioned, it's still widely used today. However, more and more value chains are switching away from TDCP to, for example, Firol HF10. It's a halogen-free, low VOC emissions-based flame retardant. One of the negative is there is a phenol that shows up in the emissions. So there are certain emissions test which has a specification for phenol. Then you have to kind of keep that in mind depending upon how much HF10 you are using. Firol PNX or PNXLE, both are very efficient in polyether form, so you need a very, very low dosage to meet MVSS 302 criteria. And particularly PNXLE, it's a low emissions. So for an example, in our experience, Mercedes has one of the stringent VOC emissions criteria per VDA 278, and PNXLE would help you meet that requirement. And Vericolapsidus, which is mainly available in Europe right now, it's basically designed for polyester foam, and it does meet the stringent humid heat aging required for the polyester foam. So again, from our product portfolio, these are the 5 products we would recommend or offer for automotive applications today. Now, if we look at the furniture foam, like I mentioned, the safety fire safety standards that drive the usage based on what how these standards are in place today. BS 5852 CRIP 5 is the only standard that requires the use of flame retardants. So FR2 was used in California 117 before 2013. But since then, it's already on the Prop 65 list. And in 2013, when they made the change in California 117 standard, and they went from uh, open flame and cigarette smoldering to just cigarette smoldering today. So there is no longer a need necessarily for a flame retardant. So we today offer PCF or PCFLO for BS 5852 CRIP 5 kind of application, and HF10 is a viable alternative to PCF or PCFLO to replace PCF or PCFLO in your formulations. Switching to rigid forms now. Again, very similar depending upon which end market. So whether it's in the US, in Europe, or in India, there are different fire safety standards that drive the use of flame retardant in rigid form. I have listed a few of the fire safety standards that's being used. So, for example, E80, ASTM E84, or UL 790, or FM Factory Mutual 4450. Those are the fire safety standards that's required for building and construction industry in the US. And then if we look at the European standards, DIN 4102, single burning item test, and there are many more new standards that's coming into the European industry as well. And some of the end applications where we see the use or we divide the rigid foam market. One being, as you can see on the slide here on the left, is the spray foam market, where liquid polyurethane foam is applied in the building and it instantly converts into the spray foam. The picture in the center is basically PIR panels that's made basically 4 feet by 8 feet coming from the factory and installed on the buildings. And then one component foam, the picture on the right, that's basically small crevices, small gaps, small areas to fill with insulating material. That's where polyurethane one component foam comes in, but that does have to meet certain fire safety standard as well. So these are the different end applications of the market where rigid PU foam goes. And looking at the innovation over the years, here you can see it's a very limited products here. At the bottom of the slide, again, I have listed the legacy products, Firewall PCF, which is the TCPP, and Firewall 6, which is a halogen-free and reactive flame retardant. But over the years, what happened is basically TCEP, which was a key flame retardant that was used in the rigid PU market for a couple of decades. And then because of the classification as a carcinogen, it got phased out in 2007. And so since then, TCPP, Firewall PCF, is the key flame retardant that's being used widely in rigid PU forms. And we also introduced Saffron 6605. It's particularly suited for spray foam and a PIR wall foam, where TCPP itself is not a good enough flame retardant to meet the fire performance criteria. So what we see is in the formulation, either you can use TCPP along with 6605, or just 6605 at a higher loading levels helps you meet the fire performance criteria. And all the challenges that I mentioned against TCPP, this would draw us for the innovation of Veriquel R100. It's basically a halogen-free and it's reactive. So, it checks off really all the things that we are looking into as a sustainable flame retardant for next generation. So Vericool R100 is what we offer today for the market. It's the flame retardant that works really well for PIR industry. So coming back to the product portfolio discussion again, PAR-PCF TCPP is the key flame retardant that's widely used for rigid foam market today. Saffron 6605, it's a proprietary flame retardant that we offer if TCPP is not good enough, PCF is not good enough in meeting the fire performance criteria. 506 is the reactive halogen-free flame retardant, and the Vericool R100 is the reactive flame retardant that we offer. So again, yeah, we are actively working today, particularly in the US and in Europe, to transfer or switch over the market from PCF TCPP to Vericool R100. Vericool R100 or TCPP free products are already in the market available today for the installation, and it is constantly growing for us. And like I mentioned, it's a phosphorus only, so it really helps us with avoiding all the challenges that TCPP faces today, and being reactive in nature, it is also sustainable over the long run in terms of not coming out of the polymer and face all the challenges that TCPP faces today. So with that, in summary, what I would like to point out is flame retardants play a key role in fire safety and the use of polyurethanes in broad range of end applications, whether it's auto foam going into the automotive applications, furniture foam, or rigid foam going into various building and construction industry related end applications. ICL has a very long history in developing flame retardants, and we continuously work on developing new flame retardants, next generation flame retardants that offers that kind of meets the growth and in the polyurethane market and needs and trends. The reactive flame retardant in ICL's product portfolio, again, Vericool R100 is the flame retardant that is available today as a TCPP alternative, and it's suitable for rigid PIR insulation and medium density closed cell spray foam insulation market. And above all, the key messaging I would point out is there are quite a bit of negative publicity out there against flame retardants, and which would have also negative impact on the use of products such as polyurethane foam, which contains flame retardant. And this negative publicity and potential for deselection of PU foam products can be avoided readily by choosing the sustainable flame retardants that are available already today. So with that, I would like to thank Snehal and Indian Polyurethane Association for giving us this opportunity to share ICL's flame retardant that's available for polyurethane industry. I would also like to thank ICL India team, Noel Peters, who is the Indian advocacy manager, and Anil Kurk, who is the country sales manager with ICL India. And I want to thank both of them as well for their help and support in making this webinar possible. With that, I'm open to have any questions, and happy to provide any further information you may need.
Yeah, thank you, Mr. Munjal, for this insightful presentation. And there are two questions in the chat box. Is TCPP, TDCP, and TCEP all are classified in the same class for scrutiny? That's the question.
So today they are not classified in the same classification. So like I mentioned, TCPP, we see the PU value chain has already moved away. So we don't see TCEP being used in the US and in Europe. We do hear once in a while that TCPP is used in China, but again, that's more of a regional thing. PU value chains in US and Europe are restricted, so they don't use TCEP today. TDCP is, again, like I mentioned, in state of California, it's a non-carcinogen, meaning you can still use it, but if the product contains TDCP in state of California, then you have to put that label saying, this particular product has a non-carcinogen. Now, that's at the state level. at the country level, at the federal level, there are quite a few things happening already against TDCP as well, but there is no restriction or ban today. Uh, but TDCP is already under scrutiny in Europe. So what we see is once something happens in Europe, it gets transferred to the US. And similarly, if something happens in the US, it gets transferred to the Europe. So it is just a matter of which region has more stricter restrictions that will get transferred to the other region. So today, I mean, TCPP and TDCP have no particular restriction in terms of that it cannot be used at all, but at the state level, at the end application level, there may be restriction that would not allow the use of such chemistries.
Okay. So there are two more questions from Mr.
Sure.
Ankush Salvi. One is any halogen-free FR available for bio-based polyester polyol technology?
For a bio-based polyester polyol technology, certainly, I can refer back to our product portfolio in the flexible, and HF10 would be the ideal for polyester foam. And certainly helps meet the automotive requirement. If you're looking at the furniture foam, HF10 would be ideal as well.
Okay, and the second part of the question is any liquid FR which comply fire standards EN 455452 for molded sheeting PU foam. Liquid FR he is asking for.
Liquid FR. Okay. Well, so currently for that particular standard, we have no viable product from our product portfolio. Meaning, some of the challenges we see with molded foam, it's mainly because of the poor hydrolytic stability. So, for an example, what I pointed out here in red, because in molded foam, you are making up the blend. You have the catalyst, the surfactant, the polyol, and flame retardant, any other additives you may have all mixed together. And once you mix together, flame retardants, particularly with poor hydrolytic stability, would start breaking down. So you will not get the shelf-life stability that you are looking for. So from that perspective, that's the challenge we see with products that we have in our product portfolio today.
Okay. Then the next question is from Mr. Agrim Thaplial. Are TEP melamines EG can be the alternatives to TCPP?
Yes, the short answer is yes. However, one thing I also want to point out is TEP, which is a non-halogenated flame retardant. It is already under scrutiny in Europe since the beginning of 2025. So the future of TEP is very limited as well. The other part is, again, TEP is a much lower molecular weight compared to TCPP. So we see that TEP would run into the same challenges like TCPP in next 2 to 5 years. If it's being used in a large amount like TCPP is used today, then it will have the same scenarios where it starts coming out of the polymer and then it gets into the environment. People will start looking at it and saying, now this is the new molecule we see a lot in air and water and fish and breast milk and human cells and all. So can it be used technically? Yes. Is it a sustainable solution? We certainly don't believe so. And that's why our approach has been a reactive flame retardant so that we can avoid all these challenges that we know it's going to come up for additive flame retardants.
Okay.
And the other, I guess the other flame retardant mentioned was melamine. The challenge, again, melamine is already a carcinogen. There's already scrutiny happening against melamine in Europe as well. Being solid, there are the value chains are looking at to get some sort of break or avoidance where they can prove with the data that even though it's there, it's no longer coming out of the polymer, it's no longer coming out of the article, and so trying to get a carve out approach here. However, we certainly don't think that it would be a long-term or sustainable solution. So that's one part, from the regulatory perspective. And on the technical part, the challenge with melamine is it's a solid in nature. So again, being solid in nature, it does create quite a bit of challenges for polyurethane processing. So you have to kind of keep that in mind as well.
Okay. And the next question from Mr. Anup Sharma is choosing a FR which will fulfill the standard and also the tris free. So what to check in FR to check both?
What was the second one? Did you say tris free, or I just want to make sure I understand it correctly?
Yeah, if Mr. Anup Sharma is there, sir, please unmute yourself and ask the question. What do you mean by tris free?
Okay, it does say tris free, right? I just wanted to make sure.
Yeah, it's a tris
Okay.
free because some of the
Okay.
customers wants a foam which is means
Yeah.
fulfill the standards and as well as tris free.
Yeah, so normally the tris free comes from the product name. So as you can see here, TDCP, which basically is named tris 1,3 dichloro, TCPP is tris, uh, TCEP, which I haven't listed here because it's no longer used, but that's also tris. So what you may hear more is the tris free. So that's what it's referring to. Basically, tris free meaning no TDCP, no TCPP, or no TCEP. So yes, in those instances, we already have in our product portfolio alternative flame retardants like HF10, PNX, PNXLE, or Vericul R100 that should help you uh, basically not have TCPP or TDCP in your formulation.
Okay. And the next question is from Mr. Prashant Kumar. Any FR which is having a OH group except halogen group?
Yes. So again, from our product portfolio, we have Vericul R100. And let me actually just go to that and I can easily point out. So from this slide here, we have a particular column here that shows the hydroxyl group or OH group. Excuse me. So, Vericul R100, for an example, has a hydroxyl value of 270. So that's a reactive part of but that shows that it's a reactive material for the polyurethane chemistry. The OH group will react with the NCO or isocyanate. Same way, Pyrrole 6 also has a 460 hydroxyl, but it has a OH group part of the molecule, so it would react in.
Okay. Now, one more question from Mr. Amol Muralidhar Rao. What percent of pyrrole is effective to achieve V0 rating, UL V0?
A good question. Thank you. So this helps me further going deep in our Pyrrole 6 molecule. So Pyrrole 6, it's a halogen free. It's reactive, and part of the molecule also has nitrogen. And as probably you are all aware that nitrogen works as a catalyst for polyurethane chemistry. Most of your catalyst has nitrogen atom part of the molecule. So what it does do for Pyrrole 6 is it puts some restriction on how much of Pyrrole 6 can you use. So for an example, typically what we see is in the PU formulations, you may have anywhere from 5 to 15 to 20 part of flame retardant to meet the fire performance criteria. Now, if you try to put 5 part of Pyrrole 6, your reaction is just gonna go a lot more faster. And so basically it brings in a lot more challenges in terms of how much Pyrrole 6 you can use in the formulation. What we normally see is Pyrrole 6 is maximum 2 to 3 parts before you start seeing a lot more impact on your uh, catalyst package or catalytic reactivity part. So that's the restriction on Pyrrole 6 that you have to keep in mind. So we have not seen formulators can use more than 2 to 3 part of Pyrrole 6 in the formulation.
Okay. The next question is from Mr. Ramakrishna from Srimalani Foam. Can we use HF10 in polyether foam in automotive grade foams as per new guidelines in India? HF10.
Yes, I believe so. I have to look into all the guidelines for Indian market, but that's one of the key flame retardant that we offer as a TDCP replacement. Like I mentioned, the negative part that we see is if you have particularly stringent emissions criteria that foam has to meet. And if it has a particular specification for amount of phenol that can be in emission, then you have to kind of keep that in mind for HF10. But besides that, I mean, it certainly works as a TDCP replacement. If phenol is an issue for your given OEMs or the end applicator market, PNX or PNX LE would be a very good solution as well.
Okay. The next question is, what is the maximum FR dosage generally used? Maximum FR dosage.
Um, Okay, so I'll give my answer in terms of end applications. So, for example, in automotive applications, we see anywhere from 7 or 10 part of flame retardant to as high as 15 part, depending upon what thickness of the foam is being used and what OEM requires. But that's the typical flame retardant dosage. In the furniture foam, particularly for BS5852 CRIP 5, where you do need to use two flame retardants together. Just one phosphorus-based flame retardant is not good enough. So typically there we see anywhere from 10 to 15 part minimum of 5-role PCF or TCPP, along with 20 to 25 part of melamine. So, if you are, and since we don't offer melamine, you still have to keep melamine as your flame retardant synergist in the formulation, but you can use HF10 at the same loading level as 5-role PCF or TCPP. In the rigid PIR or spray foam market, we see usage of flame retardant anywhere from 10 part to as high as 20 part. Again, depending upon what fire safety standard you are trying to meet.
Okay. What percent of very cool is effective to achieve ULV0 rating? Very cool.
Well, so you just scroll down there. Yes. So Vertical R100, again, if you are targeting to use for flexible foam, you would have some challenges, meaning, because of the higher reactive nature, you will have to do a lot more formulation work to make sure that you are able to make a good quality foam in flexible foam. Now, in the rigid form, it's not an issue because it's totally different isocyanate, different polyols, and so forth. Now, is this question is more related for flexible foam or rigid foam?
Okay, so Mr. Amol Muralidhar Rao Kentale, if you are hearing this question, please suggest. Hello. Hello, Amol sir, if you are there, please suggest.
It's for
No, sir,
both.
I think he has left the meeting. Okay. Okay.
It's for both.
It's for both. Okay. Yeah. So for on the rigid side, like I said, on the flexible side, you would have a lot more challenges using reactive flame retardant like R100 in terms of making a good quality foam. But on the rigid side, I would say you can start somewhere around 10 part and see what kind of performance you get, and then we can certainly uh, work with you on optimizing the FR package. There's a lot more we need to have a conversation about whether what's the density of the foam, what blowing agent you are using, and so forth.
Okay. So the next
Thank
question,
you. Thank you.
Sure.
what FR we can use for viscoelastic foam applications?
So in our experience in viscoelastic foam, again, it goes mainly for BS5852 Clip 5 application. Viscoelastic foams are mainly used for mattresses and pillows. And those are the key applications where we see where you would need to meet a fire performance criteria as well. And in such applications, we see Firewall PCF or HF10 as the flame retardant that can be used.
Okay, and then the next question is, what was the suggested HF10 dosage for 22 density FMVSS 302 foam? I mean, passing that criteria. 22 density foam.
So 22 would be on the lower end of the density range that we normally have seen for automotive foam. And for those ones, you would need somewhere around 15 part minimum to start with for HF10. And you just have to optimize based on your formulation. So, but the starting recommendation would be about 15 parts.
And the last question is, would ICL-FR generate a toxic smoke?
So any polymer that you burn, or if it's burnt in any environment, will create a toxic smoke. So whether, so for an example, if you have a polyurethane foam, whether you have a flame retardant present or not, if you burn them, it's going to start generating toxic smoke. So it's not a matter of flame retardant, it's just a matter of any organic material or polymer will generate toxic smoke.
Then the next question is from Anup Sharma again. If melamine is also about to be banned, any solid FR which will come in the picture, or simply liquid FRs will fulfill the standards like BS5852, CRIP 5, etc.
So we are currently working, we have active R&D projects where we are looking at for the next generation flame retardant for BS5852 CRIP 5 application, where we can offer melamine-free technologies. Now, there are multiple ways we have seen the value chain is approaching this. For example, polyol manufacturers are coming up with next generation polyols, which have a better fire performance, which would allow, or which could allow only liquid or phosphorus-based flame retardant use and meet the BS5852 CRIP 5. Of course, there are possibility of other solid flame retardants that can be used to replace melamine. And we are, from ICL's perspective, we are also working on developing next generation flame retardant that would help us eliminate or replace melamine in the formulations.
Okay, so I have one question that, as you said, when you use tris SFR, after some time it starts leaching out. So, I mean, how long we can take that period after 3 years or 5 years, or how much time will it will take to get leached out?
I guess there was a simple answer that, here is 5 days or 10 days or 5 months, but it all depends on the end application. So for an example, if your foam is exposed to a high airflow end application or a high temperature end application, then the potential for the flame retardant to come out would be much faster. Compared to that, if your foam is just sitting in a closed environment, it's not having any air passing through it, it's moderate or very mild temperature exposure, then that period would be much longer. So that's from the end application perspective. The other thing that we need to keep in mind is after the use. So for an example, once any given article that contains PU foam with TCPP, when it gets discarded, thrown away, how it's being treated, is it just going into the site where, all the garbage are just staying there and being dumped into the ground? Then, over the time, depending upon the rain, depending upon the temperature, again, environmental exposure, it could be faster or slower. So, I mean, simple answer is, I mean, there is no particular timeline that we can say. It all depends on the end applications and, the overall exposure to the environment.
Okay. Okay, sir. So thank you for this informative session. And we would, yeah, so yeah, this was very insightful, and I hope all the participants might have got. It was a good knowledge sharing session, and we would like to thank you on behalf of IPUA. Thank you for your time, sir.
Sure. No, thank you again. Again, Snehallataji, thank you, and Indian Polyurethane Association, thank you for giving us the opportunity. And I also want to reiterate that Noel Peters and Anil Kurup are our key contact for ICL India. So in future, if you have any questions, if you need any further information or anything, do not hesitate to reach out to Noel or Anil, and we would be happy to support any way we can to the PU association in India or any of the PU value chain members.
Thank you, sir. And also from IPUA side, we would like to thank Noel and Mr. Anil Kurup. Thank you for your help and support all the time. Thank you so much.
Thank you.
Thank you, ma'am. Thank you, Munjal.
Thank you, everyone. Have a good evening.